In this videotape, we're going to be solving systems of equations. Our main emphasis will be on systems of linear equations, but we will do a few involving nonlinear equations. We'll basically be using techniques of elimination and substitution to solve these systems of equations. Let's get started. First pair of equations. We want to solve a system (2x minus y equals 4 and x plus y equals 5). Now, this is a particularly simple system of equations to solve. It really lends itself to the elimination technique, because if we were to add the two equations, 2x plus x gives us 3x, minus y plus y, the y drops out, that is, it's eliminated, equals 4 plus 5, which is 9, and we immediately can solve for x. X equals 3. And once you know what x is, you can substitute into either equation to figure out what y is. Well, let's say x plus y equals 5, x is 3, leaving us with y equals 2. So we have as our solution, which we have to check, x equals 3, y equals 2. Let's check it. 2 times 3 is 6, minus 2 equals 4. That's correct. 3 plus 2 equals 5. That's correct. So what I've just shown you is this technique of elimination. That is, to be able to add the two equations so that one of the variables, either x or y, is eliminated. And then, having found one of the values, then to substitute into either equation to get the other one. This system could also have been solved by the technique of substitution. 2x minus y equals 4, x plus y equals 5. Now, when you're using the technique of substitution, you solve either equation for one of the variables, whichever seems to be easier to solve, and then you substitute the value that you get into the other equation to get the other variable. Let's see what we're doing. Let's say we solve the top equation for y. We would get 2x minus y equals 4. Adding y to both sides and subtracting 4 from both sides, we would get y equals 2x minus 4. Actually, it would look like 2x minus 4 equals y, and we could write y equals 2x minus 4. So I solved the first equation for y. Excuse me. Then we take this value for y and we substitute into the other equation. So we have x plus y equals 5, but y we see is 2x, excuse me, but y is 2x minus 4. See, we solved the first equation for y, then took this value for y and substituted into the second equation. So x plus y equals 5, we wrote x plus 2x minus 4, because that's what y is, equals 5. 3x minus 4 equals 5. 3x equals 9, adding 4 to both sides. X equals 3 as before. And having found that x equals 3, to substitute into either equation, let's say we plug in here. If x equals 3, we get 2 times 3 minus 4, y equals 2. So once again, giving us x equals 3 and y equals 2. Now, I admit in this particular system, it does seem much simpler to do it by elimination. This will not always be the case. There are those equations that lend themselves to substitution more readily than to elimination. Remember, in elimination, we're trying to add the equation so that one of the variables drops out. Once we get one of the variables, we substitute in and we figure out what the other one is. In substitution, we solve one of the equations for one of the variables, whichever seems easier. We could solve the first equation for y. Y is 2x minus 4. Take that value for y and substitute it into the second equation. So x plus 2x minus 4 equals 5. That led us to 3x equals 9, x equals 3, and then we substitute back into either equation to get y equals 2. Okay, let's try the following. I'm just going to write solve in each case for solve the following system of equations. Okay, x minus y equals 3. 3x plus 2y equals 4. All right. We can solve this by substitution. Let's try that. Let's solve the top equation for x. X equals y plus 3. Let's substitute that value for x into the second equation. 3 times x plus 2 times y equals 4, or 3 times y plus 3, which is equivalent to x, plus 2y equals 4. 3y plus 9 plus 2y equals 4. Collecting like terms, 3y plus 2y, 5y plus 9 equals 4. Subtracting 9 from both sides, 5y is minus 5. Dividing by 5, y is minus 1. And then if x is y plus 3, x must be minus 1 plus 3, or 2. So y is minus 1 and x is equal to 2. Here I substituted minus 1 plus 3 and I got 2. Let's check this. X minus y should be 3. 2 minus minus 1 is 3. 3x plus 2y should be 4. 3x, that's 6, plus 2y. 3x minus 2. 3x, which rather is 6, minus 2 is 4. So it checks out. So that's by substitution. We could have also done this by elimination, except it's not as easy as the last problem. If we add these equations, neither x nor y is going to drop out. Let me remind you of the first system that we solved. All we had to do is add the equations and the y's disappeared. They were eliminated. Here we're not so lucky. What we have to do here is to multiply one or both equations by some integer so that when we take the equations which result and we add them, one of the variables is eliminated. Well, in this case, we could accomplish this if we were to multiply the top equation by 2. Let's see what we would get. If we multiply the top equation by 2, both sides, we get 2x minus 2y is 2 times 3, or 6. Okay? Remember, we're multiplying both sides by 2. The left side gets multiplied by 2 and the right side gets multiplied by 2. 2x minus 2y equals 6. And then the second equation we could leave alone. 3x plus 2y equals 4. Now when you add the equations, 5x, the y's drop out, equals 10. Dividing by 5, x equals 2. And once you know x equals 2, substitute into either equation. Let's say x minus y is 3, 2 minus y is 3, and you get that y equals 2 minus 3, or minus 1, which of course the same answers that we got when we solved by substitution. X equals 2, y equals minus 1. So whichever way you would want to do it, substitution or elimination, in this problem also it didn't much matter. It wasn't as clear-cut as the last problem, where clearly elimination was the easier way. In the remaining problems, I'm just going to solve them by whichever technique seems to me to be easier. I won't be doing both of them. Let's try now problem 3. Solve the following system of equations. 3x minus 4y equals 5. 2x minus 5y equals 1. Now, substitution isn't particularly easy. It would involve fractions. You'd have to solve for either x or y, and none of them have coefficient 1, which would make it particularly easy to solve, and then substitute into the other equation. So I'm going to try for elimination. However, if you just add the equations, obviously nothing drops out. And also, we can't get by with just multiplying one equation by an integer in order to use the elimination techniques. What we have to do here is actually to multiply each equation by a different integer so that the resulting equations, when added, result in the elimination of one of the variables. Let's say I multiply the top equation by plus 2 and the bottom equation by minus 3. Let's see what happens. 2 times 3x, that's 6x. 2 times minus 4y is minus 8y, equals 2 times 5, which is 10. I multiplied both sides of the top equation by 2. Now let's multiply both sides of the bottom equation by minus 3. Minus 3 times 2x is minus 6x. Minus 3 times minus 5y is plus 15y. Minus 3 times 1 is minus 3. Now you can see why I picked the 2 and the minus 3. Because we have a 6x and a minus 6x, and when we add the equations, the x's drop out, and I get minus 8y plus 15y. 7y equals 7. Dividing by 7, y equals 1. And once I know y equals 1, I can substitute into either equation. Let's say I substitute into the first one, 3x minus 4y equals 5. 3x minus 4 times 1 equals 5. 3x minus 4 is 5. 3x is 9. X is 3. So I have x equals 3, y equals 1 as a solution of this system of equations. Let's check that. 3 times 3, 9. Minus 4 is 5. 2 times 3, 6. Minus 5 is 1. Okay, so I did this by the elimination technique. And sometimes you can do better, but what I did was to multiply the first equation by the coefficient of the second, and the second equation by the negative coefficient of the first variable in the first. I used the 2 here and the minus 3 here to produce the 6 and the minus 6 coefficients. Okay. In example number 4, we have the following. Solve the system of equations. X over 2 minus y over 3 equals 2. X plus y over 2 equals 11. Okay, now once fractions are involved, what I'm going to do is to start by eliminating the fractions. That will turn it into 2 equations similar to the ones that I've handled before. And then I will do them by whichever technique seems to work better. To eliminate fractions in the first equation, I'm going to multiply by 6, which is the lowest common denominator. And in the second equation, I'm going to multiply by 2. Multiplying the first equation through by 6 gives me 6x over 2, which is 3x, minus 6y over 3 minus 2y is 12. And in the second equation, I get 2x plus 2 times y over 2 plus y equals 22. All right. To do elimination here, you could do either elimination or substitution. If you want to do by elimination, you can get by with just multiplying the second equation by 2, because I notice that there is one variable whose coefficient is 1. So that gives me, rewriting the top equation, 3x minus 2y is 12. Multiplying through the second equation by 2, 4x plus 2y equals 44. And adding, I get 7x, the y's drop out, equals 56, and dividing by 7, x equals 8. Once I know that x is equal to 8, I can substitute into either equation. Let's say I substitute into 2x plus y equals 22. X is 8. So I get 16 plus y is 22, and y is 6. X is 8 and y is 6. Let's check in the original equation. X is 8, y is 6. 8 over 2, that's 4, minus 6 over 3, that's 2. 4 minus 2 is 2, that's correct. And x, which is 8, plus 6 halves, 8 plus 3 is 11, so that checks out. Okay, now for my next example, I want to solve a system of linear equations, but this time involving 3 variables, x, y, and z. This is now example number 5. Solve the system of equations that I'm giving you. X plus y minus z equals 2. 2x plus y minus 3z is 1. X minus 2y plus z equals 3. Let's label the equations 1, 2, and 3. Okay, now, the way we handle a problem like this is to use elimination. What we're going to do is pick a pair of equations and eliminate one of the variables from that pair of equations. Then pick a different pair of equations and eliminate the same variable from that pair. That will reduce the system to 2 equations and 2 unknowns, which we already know how to solve. So let's start by eliminating the variable z from equations 1 and 2. To do that, let's see, I have x plus y minus z is 2, and 2x plus y minus 3z is 1. I can accomplish that by multiplying the top equation by minus 3. Took equations 1 and 2, and I'm going to eliminate z by multiplying the top equation by minus 3. That's minus 3x minus 3y plus 3z is minus 6, being sure to multiply each term by the minus 3. Minus 3x minus 3y plus 3z is minus 6. And then underneath, 2x plus y minus 3z is 1. Adding the equations, we now get minus 3x plus 2x minus x, minus 3y plus y minus 2y, the z's drop out, equals minus 5. Okay, let's just keep that there. Now I want to pick another 2 equations and eliminate z from them. Well, I've already used 1 and 2, this pair. I can use either 2 and 3 or 1 and 3. I'm going to use 1 and 3 because I can eliminate z simply by adding the equations. So let's also eliminate z from equations 1 and 3. Either 1 and 3 or 2 and 3. Well, 1 is x plus y minus z is 2. And 3 is x minus 2y plus z is 3. And here all you have to do to eliminate is to add 2x minus y equals 5. So we take these 2 boxed-in equations, and we have 2 equations and 2 unknowns. We have 2x minus y equals 5, and the other one, minus x minus 2y is minus 5. And I'm going to take these 2 equations and 2 unknowns and solve. Now I'm going to do this by the elimination method. Let's multiply this equation by 2. Leave alone the first one. We get 2x minus y is 5. Multiply this one by 2, and you get minus 2x minus 4y is minus 10. Now add, the x's are eliminated, and I get minus 5y is minus 5. Or dividing through by minus 5, y equals plus 1. Once I know that y is plus 1, go to one of the equations involving only x and y, substitute in this y value, and figure out what x is. Well, y is 1. 2x minus y is 5. 2x minus 1 is 5. 2x is 6. I now know x is 3. Y is 1 and x is 3. Now go back to one of the original equations. You know x and y, and figure out what z is. Let's say we take the first equation. X plus y minus z is 2. But I now know x is 3, y is 1, and I want to solve for z. 4 minus z is 2. Minus z is minus 2. Multiplying both sides by minus 1, z is plus 2. So I have for my solution x equals 3, y is 1, and z is 2. Let's check and see if it's correct. 3 plus 1, 4 minus 2 is 2. 2 times 3 is 6, plus 1, 7, minus 6 is 1. 3 minus 2, that's 1, plus 2 is 3. Let's go over what we did. We have 3 equations and 3 unknowns, 3 linear equations and 3 unknowns, x, y, and z. I picked a pair of equations, and I decided to eliminate one of the variables from that pair. I picked arbitrarily to eliminate z from equations 1 and 2. Having decided to eliminate z, I now have to eliminate z from another pair of equations. Well, we've already used 1 and 2, so either 2 and 3 or 1 and 3. But I noticed that 1 and 3 would be very easy to eliminate z from. All you have to do is add them. So I did that. And I had, when I eliminated z from 1 and 2, I got this equation in x and y. And when I eliminated z from 1 and 3, I got this equation in x and y. Now I have 2 equations in x and y. I multiplied this equation by 2 and was able to solve by elimination, figure out what y is, then substitute back into either of these to figure out what x is. Now, knowing x and y, I can go back to one of the original 3, knowing x and y, and just solve for z. So you just have to keep in mind always which variable you're eliminating. Okay, you don't want to eliminate z from one and x from the other. It can get confusing. If you're going to eliminate z, pick 2 equations, eliminate z, pick another 2 equations, eliminate z, and then solve 2 equations and 2 unknowns. Okay, we're up now to example number 6. And I want you to evaluate the following determinants. In part A, we have determinant 4, 2, 3, 5. And in part B, determinant 5, minus 1, 8, minus 2. Now I want to remind you that if you have the determinant A, B, C, D, this is defined to be AD, the product of the numbers on the diagonal, minus BC, minus the product of the other 2 numbers. AD minus BC. All right. So the product of the numbers on this diagonal, 4 times 5 minus 2 times 3. 20 minus 6, or 14. And similarly, over here, 5 times minus 2, the product of the elements on the diagonal, minus 1 times 8, minus 10, minus a minus 8. That's minus 10 plus 8, or minus 2. Multiply the numbers on the diagonal and subtract the product of the other 2 numbers. Okay, now, using determinants and Cramer's rule, it is possible to have another way of solving systems of linear equations. And what I'd like to do is to use Cramer's rule to satisfy, to solve rather, excuse me. Using Cramer's rule, it's possible to solve the following system of equations. Use Cramer's rule to solve the system 3x minus 4y equals 5, 2x minus 5y equals 1. 3x minus 4y equals 5, 2x minus 5y equals 1. In order to solve a system of equations, 2 by 2 system of equations by Cramer's rule like this, we have to first calculate 3 determinants: d, d sub x, and d sub y. D would be the determinant formed by detaching the coefficients from the left sides of the equations. 3 minus 4, 2 minus 5. 3 minus 4, 2 minus 5. Eliminate the ignore the variables x and y, just write down the coefficients. The x variables coefficients, the y variables coefficients. dx and dy, okay, are also 2 by 2 determinants. However, for dx, we use the same y column. However, the x column is replaced by the right-hand side. And for dy, we use the same x column as d, but the y column is replaced by the right-hand side. So let's go over that. Using only the coefficients of the variables x and y, we get d, the determinant here. dx, we start with this. However, we replace the x column, the first column, by the right-hand side, 5, 1. dy from d, we use the same x column, but we replace the y column by the right-hand side. Now we have 3 determinants to evaluate. 3 times minus 5 minus minus 4 times 2. 3 times minus 5 minus minus 4 times 2, which is minus 15, plus 8, which is minus 7. Here we get 5 times minus 5 minus minus 4 times 1, minus 25 plus 4, which is minus 21. And finally, 3 times 1 minus 5 times 2, which is 3 minus 10, or minus 7. The x and y values of the solution are given by the following. X is dx over d, y is dy over d. So to solve this system, we simply say x is dx over d, minus 21 over minus 7, and y is dy over d, minus 7 over minus 7, giving us x is plus 3 and y is plus 1. X is plus 3, y is plus 1. Now I want to have you recall problem 3, which we did earlier on this videotape by elimination. That was the same system of equations. 3x minus 4y is 5, 2x minus 5y is 1. We did this earlier by elimination, and we get x equals 3, y equals 1 as the answers. Okay, and here you're seeing it done by Cramer's rule. Of course, you could just, and you can check this. It does work out. We did that earlier. 9 minus 4 is 5. 6 minus 5 is 1. Okay, so here you calculate d, dx, and dy, and then x and y are given by these formulas. That we have solved so far were systems of linear equations. I now want to introduce some nonlinear equations. We want to solve the following system. X squared plus y squared equals 25. X minus y equals 1. Now, when we were solving systems of linear equations, basically we were, if you were to graph the equations, we'd be graphing two straight lines. And in all of the examples we had so far, the two straight lines intersected at a point, and that was the solution. Of course, we should bear in mind that two straight lines might not intersect at all, in which case, they could be parallel, in which case there would be no solutions. Or two straight lines could actually fall on top of each other, in which case every point on the line would be a solution to the system of equations. Okay? When we're solving a system that has a linear and a nonlinear equation, or two nonlinear equations, it might be helpful to make sketches of the curves to have an understanding of what's going on. Now, in the last videotape, we reviewed sketching curves of these types, and we know that x squared plus y squared equals 25. X squared and y squared both appear. Their coefficients are the same, and this is the equation of a circle. Center at the origin, radius 5. It's supposed to be, anyway, a circle. The other one, since x and y are both to the first power only, this is going to be the equation of a straight line. If y is 0, x is 1. If x is 0, y is minus 1. And it looks something like this. Now, what we're trying to do is to find the points of intersections of these two curves. It appears that there will be 2 points of intersection. And let's see if we can get them algebraically. You might even be able to read them more from the graph, but we prefer to do this algebraically. Now, there are no like terms. We have x squared, y squared, x and y. So the elimination method doesn't seem like a particularly good idea. Instead, we can solve without too much difficulty for x in terms of y, so we're going to do it by substitution. Use substitution. X minus y equals 1, so x is y plus 1. Substitute that value for x into the original equation. X squared plus y squared equals, the first equation, x squared plus y squared equals 25. We get y plus 1 squared plus y squared is 25. Y squared plus 2y plus 1. Y plus 1 squares out to y squared plus 2y plus 1 plus y squared is 25. 2y squared plus 2y plus 1 is 25. Subtracting 25 from both sides. 2y squared plus 2y minus 24 is 0. Divide both sides of the equation through by 2. Y squared plus y minus 12 is 0. Y squared plus y minus 12 is 0. This can be solved by factoring. Y, we need two numbers which multiply to minus 12 and add to plus 1. And they would be plus 4 and minus 3. Checking, we'd have y squared minus 3y plus 4y. That's plus y minus 12. Y equals minus 4. Y equals 3. As the y coordinates of the points of intersection. Now remember, x is y plus 1. So from over here, x is y plus 1. So minus 4 plus 1 is minus 3. 3 plus 1 is 4. And you can check these points. We have minus 3, minus 4, and 4, 3. Checking in here, minus 3, minus 4, and 4, 3. We have 9 plus 16 is 25. Minus 3 plus 4 is 1. 16 plus 9 is 25. 4 minus 3 is 1. And by the way, looking at the picture here, 4, 3 is this point over here. 1, 2, 3, 4, up 3. and minus 3, minus 4 is around here. So we were able to find the 2 points of intersection that the graph indicated. Of course, we prefer to use the algebraic solution because if this did not come out to be whole numbers, or if your picture was not particularly accurate, you would not be able to read it off carefully from the graph. Okay, let's solve the following nonlinear system of equations. We have 4x squared plus y squared is 4. X squared plus y equals 1. Now here there is a like term, the x squared. So if you want, you can solve this by elimination. That is, you can multiply the second equation by minus 4. The first equation we're going to leave alone. And the second one we're going to multiply through by minus 4. Minus 4x squared minus 4y is minus 4. And then we're going to add. The x squareds go. We have y squared minus 4y equals 0. When we add the equations, y times y minus 4 is 0. Y is 0. Y is 4. And let's see what we have. Y is 0, y is 4. X squared plus y is 1. So y is 1 minus x squared. Well, again, we should do it this way. X squared is 1 minus y. So if y is 0, x squared is 1 minus 0, x squared is 1, x is plus or minus 1. And if y is 4, x squared is 1 minus 4, x squared is minus 3, and there's no solution from this, because you cannot solve for x. So what are we left with? We're left with 2 points, 1, 0, and minus 1, 0. In other words, y is 0, and x can be either plus or minus 1. When y is 4, we were not able to solve for x. And if we make a sketch here, we can understand what's going on. The first equation is an ellipse. Notice that the coefficients of x squared and y squared have the same sign, but they're not equal. If y is 0, x squared is 1, x is plus or minus 1. And if x is 0, y squared is 4, y is plus or minus 2. And the ellipse looks like this. The other one is a parabola. Notice that x is squared, but y isn't. Furthermore, it is missing the x term, so the axis of symmetry will be the y-axis. If x is 0, y is 1. If y is 0, x is plus or minus 1. So we have this parabola. And we do see that the only points of intersection are 1, 0 and minus 1, 0. Okay, in example number 10, we want to sketch the solution of the following system of inequalities instead of equations. And we have 2y minus x is less than or equal to 2. X plus y greater than or equal to 1 and x minus y less than or equal to 1. Let's number them 1, 2, and 3. In an earlier videotape, we learned how to sketch the graph of a single inequality. Now what we're going to do is to look for the intersection of the various solution sets and to shade that in, and that'll be the solution to the system of inequalities. In each case, we're going to sketch the graph of the corresponding equation and then pick a testing point or a checkpoint to determine which half plane is included, and then we'll look to see the intersection. Okay, let's see what we get. Let's make a little table of values for each of these as straight lines. For 2y minus x equals 2, for x plus y equals 1, and x minus y equals 1. Here, if x, these are all straight lines, if x is 0, y would be, 2y is 2, y would be 1. If y is 0, x would be minus 2. So, okay, here, if x is 0, y is 1. If y is 0, x is 1. And here, if x is 0, y is minus 1.